Good morning, dear students. Today we'll discuss the construction principle and working of a moving coil galvanometer. So, a galvanometer is a device used to detect the presence of electric current in a circuit. So, here first we will discuss the principle of a moving coil galvanometer. In the previous class, we have discussed about the torque, isn't it? So, here the working of a moving coil galvanometer is based on the fact that when a current carrying coil is placed in a magnetic field, it experiences a torque. Okay, so that's the principle of moving coil galvanometer. Now let's discuss the construction of a moving coil galvanometer. You have to understand each parts of the moving coil galvanometer and their function. First of all, a moving coil galvanometer consists of a set of coil. You can see rectangular coil in the middle, okay, and it is suspended between the pole pieces of a powerful horseshoe magnet. You can see that north and south poles, which are concave in shape, and the rectangular coil is placed in between. And this powerful horseshoe magnet is there, which provides the magnetic field. The other end of the coil, you can see, it is attached to a light phosphor bronze spring, and a mirror strip you can see on the top M is fixed on the suspension fiber so that reading can be taken using lamp and scale arrangement. Then inside this coil, a soft iron cylinder is placed. So you know why you are using soft iron, as it will get magnetized easily. The plane of the coil is always parallel to the field, whatever be the position of the coil. Understood? The plane of the coil, here you have a rectangular coil, and the plane of the coil is always parallel to the field. Field you know, from north to south. Whatever be the position of the coil, such a manner is known as radial magnetic field. And if there is radial magnetic field, it will increase the strength of the magnetic field also. That's the purpose of using a soft iron core. Okay, so that's all about the. So this is the top view. Okay, that is the north pole and south pole, and this is the soft iron core top view. So this will turn the field like this. Look here, this type is known as radial field. Okay, that means the plane of the coil is always parallel to the direction of magnetic field. That is called radial field. Now we will check the working of the galvanometer. So, working. So in the figure you can see a coil, and let the coil be named as PQRS. Okay. This coil is suspended freely in the magnetic field. You suppose that. And in this coil, here you can see like this. Okay, suppose the name of the coil is P, Q, R and S. Okay. Since it is a rectangular coil, here we consider this PQ as the length, which is equal to L, and this QR is taken as the breadth. Okay, QR is taken as the breadth B. Clear? Now, let us consider there are n number of turns in the coil, and area of each turn of the coil is considered as area is equal to length into breadth. Clear for you? So here let L be the length PQ or RS of the coil. Then B be the breadth for QR or PS of the coil. Then capital N is the number of turns in the coil, and area of the coil is taken as length into breadth. Suppose in this particular magnetic field, let B, capital B, be the magnetic field in which the coil is suspended, and you can see I current is passing through the coil in the direction PQRS. Okay, in the diagram it is clear that I amount of current is passing like this from PQRS like that. Okay, so this is all about the basics. Now, at any instant, let us consider an angle alpha. Okay, alpha is an angle which normal drawn on the plane of the coil makes with the direction of magnetic field. That means at any particular, when this rectangular coil rotates, at any particular point, it makes an angle alpha. Okay, with the direction of magnetic field. You know that because in the last class also we have seen while we discussed torque, that torque sometimes it comes parallel while rotation, sometimes it will make an angle theta or alpha like that. Okay, here we have taken the angle as alpha, which the plane of the coil, normal drawn on the plane of the coil, makes with the direction of magnetic field. So what will happen is when it rotates like that, surely there will be a torque experienced by the coil, and the torque you have seen that it is N A B I sine theta. Here it is alpha, so I will write it as sine alpha. So this is the expression for torque. And due to this deflecting torque, what will happen? The coil rotates. Okay, the coil rotates and the suspension wire gets twisted. So because of torque, the coil rotates, the suspension wire gets twisted, and what will happen when it rotates to one side? A restoring torque is set up in the suspension wire. Restoring means what? You have studied restoring force while you have studied the stress, strain, etc. You have studied that. That means it is something developed inside. So when this rotates, when this suspension fiber also gets rotated or also get twisted, there is a restoring torque set up in the suspension wire. Okay, so restoring torque is developed because of the torque produced. Okay, so at that time I already told that there is a phosphor bronze strip at the top. You can see a phosphor bronze strip, and in that phosphor bronze strip you can note the deflection. That is, let us consider it as theta. So while it twists, we can note a twist theta produced in the phosphor bronze strip due to the rotation of the coil. And I told that here a restoring torque is developed, which we can represent as K. Okay, this much is clear for you. So once again I will tell, here we have considered the coil PQRS. It is suspended freely in the magnetic field. Here it is a rectangular coil, so its length is L and breadth is B. So area will be L into B, and total number of turns is taken as capital N. So here B is the strength of the magnetic field in which the coil is suspended, and I is the current passing through the coil in the direction PQRS. So at any instant, let alpha be the angle at which the normal drawn to the plane of the coil makes with the direction of magnetic field. Okay, that means while it rotates, it makes an angle alpha, and this rectangular coil will be experiencing a torque which is given by the expression tau equal to NABI sine alpha. Due to this torque, due to this deflecting torque, the suspension wire also get twisted, and as a result restoring torque, which we represent using the letter K, is developed in the wire. Now there is a phosphor bronze strip at the top. Okay, that means here you have a mirror. Okay, mirror, and then it is connected to a phosphor bronze strip here. Okay, this phosphor bronze strip is used there in order to identify or detect the twist produced. So it is noted that theta amount of twist is produced in the phosphor bronze strip due to the rotation of coil, and K is the restoring torque. Okay, so how will you find the total restoring torque produced? Total restoring torque. So for each unit twist, K is the amount of restoring torque. Okay, so if theta is the twist produced due to the rotation of the coil, then you can write total restoring torque is equal to K into theta. Okay, K is the restoring torque per unit twist of the phosphor bronze strip, and theta is the twist produced in the phosphor bronze strip due to the rotation of the coil. So total restoring torque is equal to K into theta. Okay, now in the equilibrium position, you know this deflecting torque or the torque produced due to the rotation, that is called deflecting torque, must be equal to what? Restoring torque. Okay, so deflecting torque must be equal to restoring torque. Now it is NIBA, okay, which is equal to K theta. And the maximum torque only we are taking. At that time alpha is equal to 90. So NIBA sin 90, sin 91. So NIBA is the result, that is K theta. Okay. So what is I from this expression? I is equal to K theta divided by NBA. Clear? Now this K by NBA, all are constants, right? So K by NBA is a constant which we denote as G. It is G theta. Clear? G theta. And this G is called the galvanometer constant. So if this is a constant, I can write I proportional to theta, isn't it? So the deflection produced is directly proportional to the current flowing through the galvanometer. That is why when the current is passing through the circuit or passing through the galvanometer deflects. Understood? So when current is passing through the galvanometer, deflection is produced. More current, more deflection. I is proportional to theta. Clear? So this means that the deflection produced is proportional to the current flowing through the galvanometer. Clear? Next we have to discuss a term called current sensitivity. Okay. So current sensitivity is defined as the deflection per unit current. Deflection per unit current flowing through it. Deflection per unit current flowing through it, and it is given as IS, okay, current sensitivity, which is equal to deflection is theta by unit current I, theta by I. Okay, so theta, you know the value. What is the value for theta? Theta is equal to, you can write it as theta by I. You can take from this expression because you have the expression like I is equal to K theta by NAB, isn't it? This expression you have derived right now. So from this, what is theta by I? Theta by I is equal to NAB by K. NAB by K. So here you can write it as NAB by K. Okay. So current sensitivity, how can you increase the current sensitivity? It can be increased by increasing the number of turns. Or you can increase by increasing the area of the coil. You can increase it by increasing the magnetic field or by decreasing the torque per unit twist. Understood? So this is the way how we are increasing the current sensitivity. Similarly, we have voltage sensitivity, which can be defined as the deflection per unit voltage. Deflection produced per unit voltage. Okay, that is, you can write it as Vs, that is voltage sensitivity, which is equal to deflection theta divided by V. Okay, now what is V in terms of current? S. V equal to I into R, isn't it? Also theta, from this expression, theta is equal to NAB by K into I. This is theta. So substituting here, it will be NAB by K into I divided by IR. Okay, so I get cancelled and it is NAB by KR. NAB by. So next term is figure of merit of a galvanometer. This is actually a practical that you are doing in our lab. So figure of merit means it is the current, okay, the current required to produce a deflection, 1 millimeter on a scale kept at a distance of 1 meter from the mirror. 1 meter from the mirror. Okay, so its unit will be ampere per division. So the current required to produce a deflection of 1 millimeter on a scale is said to be the figure of merit of a galvanometer. Okay, so next is, you know about ammeter. Ammeter is a device which is used to measure the amount of current, isn't it, in the circuit, and a moving coil galvanometer is used to detect the presence of current. So a galvanometer can be converted to ammeter. That is, by connecting a low resistance. This low resistance we call it as shunt. Okay, connecting a low resistance called shunt in parallel to the galvanometer, we can convert galvanometer to ammeter. Understood? So if this is the galvanometer, we have. Now I am going to connect a small resistance, that means a low resistance, in parallel to this galvanometer. Okay, so that this particular setup is said to be an ammeter. Understood? So this is called the shunt, and the whole setup will perform the function of what? An ammeter. Okay, so first of all, you know, through galvanometer there is a current. Galvanometer itself has a resistance. So this galvanometer, suppose if it is having a resistance of G, and the current passing through the galvanometer is Ig, and let Is be the current passing through the shunt. Okay, so Is and Ig are there. Now I is the main current. That means if I current enters into this particular circuit, so that it splits into Ig as well as Is, since it is parallel. Okay, Ig is the current passing through galvanometer and Is is the current passing through the shunt. Now since they are in parallel, you know, voltage will be same in parallel connection. That is, potential difference across the galvanometer is equal to potential difference across the shunt. Okay, that is, how will you measure the potential difference or potential drop there? That is, you know, V is equal to I into R. So for the galvanometer, it is Ig into G, and for the shunt, it is Is into that particular value S. Understood? So the resistance of this shunt is taken as S. So Is into S will give you the potential difference across shunt, and Ig into G will give you the potential difference across galvanometer. So you can substitute the value, that is Ig into G is equal to Is into S. Now you know this current I is split into two, that is Ig and Is. So I can write I is equal to what? Ig plus Is. Okay, Ig plus Is. Or from this expression, Is is equal to I minus Ig. Clear? For this value Is, I can substitute this value. So, Ig into G is equal to I minus Ig into S. Okay. Now from this expression, what is S? S is equal to Ig divided by I minus Ig into G. Ig by I minus Ig into G. Clear? And what about the effective resistance? Because here both the resistance are in parallel. So the effective resistance means 1 by G plus 1 by S, isn't it? So 1 by G plus 1 by S. So that you will get GS by G plus S. Okay, this effective resistance is very, very small also, since it is in parallel connection. You know, ammeter is always connected in series in a circuit. Why? Because the resistance of ammeter is very low, so it does not change the resistance in the circuit and hence gives the true current in the circuit. Okay, so when an ammeter is connected in series, you know the effective resistance is added up, and if the resistance of ammeter itself is very low, then the total resistance is low, and as a result you can measure more amount of current. Understood? So that is why ammeter is connected in series. So in this case, we are converting a galvanometer into ammeter by connecting a low resistance in parallel with the galvanometer. So if the resistance or the shunt is connected in parallel to galvanometer, the voltage drop across both will be same. So we are taking the condition like this: Ig equal to Is into S. Also, the main current is split into two, that is Ig and Is. So from this expression we get I is equal to I minus Ig, and substituting the value here, you got the value for the shunt resistance, which is S equal to Ig by I minus Ig into G. Clear? So here when you find the effective resistance, it will be very small, and only if the resistance is very small you can measure the true current in the circuit. Okay, so next is conversion of galvanometer to voltmeter. Okay, you know a voltmeter is a device which is used to measure the potential difference in a circuit, and it is always connected in parallel to the 2 points across which we are measuring the potential difference, isn't it? Always ammeter is connected in series and voltmeter is connected in parallel. And here a moving coil galvanometer can be converted to voltmeter by connecting a high resistance in series with it. Okay, we just seen that ammeter, for converting galvanometer to ammeter, we are connecting a low resistance in parallel to it, but here we are using a high resistance in series to the galvanometer. So the diagram goes like this: we are connecting a resistance, it is a high resistance, and it is connected in series with the galvanometer. Okay, so this galvanometer has a resistance. Then this is a resistance wire having high value. Okay, and these are the points across which we want to measure the potential difference. Okay, so here also we can consider the current flowing through this galvanometer is taken as Ig, and it is having a resistance G. Okay, here we are connecting a resistance, high resistance, which we denote as R, and this is required to convert it into a voltmeter. Okay, now here how can you write the expression, the potential? This V must be equal to what? V must be equal to Ig into G plus R. Ig into G plus R, isn't it? Because the total amount is added up. Okay, the potential is added up. So Ig into G plus R. From this, what is R? R is equal to V by Ig, V by Ig minus G. V by Ig minus G. Okay. Now you can see that here it is connected in series. So the effective resistance will be very large. And for manufacturing a voltmeter, the effective resistance should be very large enough. Okay. So here, since they are added up, the effective resistance is taken as very large. So G plus R is very large. Now, as I told, a voltmeter, an ideal voltmeter should have high resistance so that it does not draw an appreciable amount of current from the circuit. Okay. So here the current does not change when the voltmeter is connected, and hence we are connecting a voltmeter in parallel. Understood? So in this way we can convert a galvanometer to ammeter. So these topics are also very important. So starting from moving coil galvanometer, we have studied the use, then the principle, construction, working, then the terms related to that like current sensitivity, voltage sensitivity, then figure of merit, and finally how to convert a galvanometer to ammeter as well as to a voltmeter. Okay, so go through all the topics, study it thoroughly. So have a nice day and thank you.